This picture is a famous painting by Manet. One of the interesting things about it is that so much of the picture is in a reflection. So we see everybody that's in this bar, and even the person who's viewing it, in the reflection of the picture. In this particular lecture, we're going to learn more about reflections and the way light behaves on large scales, where the objects that it interacts with are much larger than the wavelength of light. This is called the ray model of light. And the basic idea is that even though we know light travels as a wave, we can just treat it as traveling in a straight line as indicated by a ray like that. Sometimes this is called ray optics. So there are a few key ideas about how light travels, and you've probably heard many of these before. First off, each area of a surface of most ordinary objects scatters incident light rays in many directions. As a result, anyone who has a line of sight towards the object can see it. In other words, if I have a totally dark room and I have just this little square of paper somewhere, and then I shine a light on it. Light comes in one direction. For most objects, that light will shine out in all directions after it's reflected off of the object. That's actually very important, because that way anybody who's got a line of sight, so there's an eyeball, will have some light from here reaching their eye. I could draw another eye over here. Some light will reach it. So anyone that's got a clear line to the object can see the object. Second, objects with very smooth surfaces, like polished metal, can act as mirrors and reflect a light ray in a single direction rather than scattering it. In other words, if instead of having a piece of paper there, I had a mirror, then the light would just come in and scatter off at a single direction. If it's a totally dark room and this light is, say, a laser, then someone sitting over here might not see that beam at all, because the laser beam just goes up beyond them. Normally, if you shine a laser beam in a dark room, you don't see the beam itself because none of that light is entering your eye. Next, what happens for a transparent medium? Well, a transparent medium that's uniform, like glass, plastic, air, water, light will travel in a straight line inside those, just like it travels in a straight line in a vacuum. But when we cross from one medium to another, then we can get a change in the angle. So that would look like this. If I have a block of some material, maybe glass, and I shine some green light at it, it can actually turn direction and then go on. So the direction will change when you go from one medium to another. And the last key idea about the propagation of light: when your eye receives neighboring rays of light that are diverging slightly, they're coming apart a little bit, your brain assumes that the rays are coming from a common point. And that's how you'll construct a visual model of your surroundings. So For example, let's consider this situation, but let's look at it a little more closely. I've got a small object down here, and I light it up with some light. Now light gets scattered off in all different directions. Now, if your eye is over here, light from several different directions is going to come into your eye. And your brain just extrapolates that line of light backwards to where it originated. So it assumes the particle is right here. Sometimes we're going to find we can trick the eye. So maybe, in reality, light's coming off from a point here, but we put a lens in the way. We can put a diverging lens like that. And that'll make the light spread out. And now, if your eye is over here, it follows these diverging lines backwards to where they all cross, and thinks the particle was here, not where it really is, back here. So your eye, all it does is follow the diverging rays back to where they started. And wherever those diverging rays would have crossed, that's where your eye assumes the object is. That place where all the diverging lines cross, that's called the image position.